Have you ever wondered what it would feel like to witness a race across the solar system? Not between spacecraft built by human hands, but between ancient wanderers that have traveled for millions of years just to converge on our sun at this precise moment in cosmic history. Tonight, as you settle into peaceful rest, we'll explore one of the most remarkable celestial competitions ever observed, a cosmic chase that's rewriting our understanding of what moves through the darkness between stars. In the gentle depths of space, where silence reigns and time moves with the patience of eternity, something extraordinary is unfolding. Two objects born in different corners of the galaxy are racing toward our sun in what astronomers are calling an unprecedented convergence. Their paths through the void have been calculated with mathematical precision, yet their arrival seems to defy the random nature we expect from cosmic encounters. The first traveler, designated 3I Atlas, emerged from the constellation Lyra in August 2025, detected by the same automated survey systems that have been quietly cataloging the night sky for decades. This interstellar wanderer carries the unmistakable signature of an object born around another star, a true alien visitor making its singular passage through our solar neighborhood. Its hyperbolic trajectory tells a story of incredible velocities and vast distances, marking it as only the third confirmed interstellar object in human history. But 3I Atlas wasn't meant to journey alone. In late September, as astronomers were still marveling at their exotic guest, another visitor announced its presence with a brilliant display that transformed evening skies. Comet D 2025. T1, discovered through the combined observations of amateur astronomers in 3 different countries, materialized from the outer reaches of our own solar system like a cosmic lighthouse suddenly illuminated in the darkness. What makes this convergence truly remarkable isn't just the timing, though the mathematics of 2 significant objects arriving within weeks of each other should occur perhaps once every several million years. It's the precision of their choreography, the way their trajectories seem almost deliberately coordinated to create the most scientifically valuable viewing opportunities possible. Before we continue this cosmic journey together, I'm curious, where in the world are you listening from tonight? Are you gazing up at these same stars from a bustling city, a quiet countryside, or perhaps somewhere I haven't imagined? Please share your location in the comments below. Your perspective adds to our global community of cosmic explorers, and I'd love to know you're part of this adventure across space and time. If you find peace in these celestial stories, consider subscribing and letting the gentle chime of notifications remind you when new cosmic mysteries await your discovery. Now, let's drift deeper into the tale of these ancient wanderers. As we drift deeper into this cosmic narrative, let your mind wander to the vast scales of space and time that brought these travelers to our doorstep. The story written in their light carries information that has been preserved across distances so immense that they challenge human comprehension. 3I Atlas has been journeying through the interstellar void for potentially millions of years, its surface slowly transformed by cosmic rays and microscopic impacts from interstellar dust. Every molecule now escaping into space as it approaches our sun carries chemical signatures from its birth system, a distant stellar nursery where different temperatures, pressures, and elemental abundances created compositions unlike anything familiar from our local cosmic environment. The spectroscopic analysis reveals a fascinating chemical portrait. Unlike its predecessor visitors, 3I Atlas shows strong emissions from chromium and vanadium, elements that glow with distinctive wavelengths when excited by solar radiation. These metallic signatures create part of the object's subtle blue-green coloration, a hue that sets it apart from the more familiar green tints typically observed in comets from our own solar system. What puzzles researchers is the absence of expected companion elements. In natural samples throughout the universe, chromium and vanadium typically appear alongside titanium and manganese in ratios that reflect the nuclear fusion processes occurring in stellar cores. Yet 3I Atlas displays these refractory metals in concentrations that suggest either formation in unusually extreme stellar environments or processing through mechanisms that operate beyond our current understanding of cosmic chemistry. Meanwhile, Comet D2025T1 serves as a perfect counterpoint to this interstellar mystery. This magnificent visitor from our own Oort cloud follows every prediction with textbook precision. Its tail development and spectral evolution matching computer models with the kind of accuracy that validates decades of cometry science. Its brilliant display stretches across nearly 4 degrees of sky, roughly 8 times the apparent diameter of the full moon, creating a spectacular backdrop against which the more subtle mysteries of 3I Atlas play out. The amateur astronomical community has embraced both objects with unprecedented enthusiasm. Social media platforms overflow with time-lapse photography capturing the gradual evolution of Comet D2025T1's magnificent tail, while more specialized observers document the subtle changes in 3I Atlas's coma structure using equipment that would have been considered professional grade just decades ago. Let your thoughts drift now to the mathematical elegance underlying this cosmic convergence. In the vast theater of space, where objects move according to the precise choreography of gravitational mechanics, the probability of witnessing what we're seeing above our heads defies comfortable explanation. 3I Atlas approaches our Sun on a trajectory that will bring it closest to our star around November 15, 2025, at a distance of approximately 1.2 astronomical units, just slightly farther than Earth's orbital radius. This represents the closest approach to our Sun ever recorded for an interstellar visitor, providing unprecedented opportunities for detailed observation during its most active phase. Comet D2025T1 reached its own perihelion on October 8th, diving to within 0.4 astronomical units of our star before beginning its outward journey. Now it approaches its closest point to Earth on November 3rd, when it will pass within 0.31 astronomical units of our planet, close enough for backyard telescopes to reveal details in its coma structure and tail development. The energy requirements that brought 3I Atlas to this moment stagger the imagination. To achieve its current velocity profile from the nearest possible stellar systems would require ejection forces that push beyond what typical planetary formation chaos can reasonably explain. Even the most violent stellar encounters, the kind that can disrupt entire planetary systems, rarely impart the excess velocities needed to account for this visitor's kinetic energy signature. The precision of timing becomes even more remarkable when you consider the navigational accuracy required. Most objects ejected from other stellar systems should approach from arbitrary directions, their paths determined by the random gravitational encounters accumulated during millions of years crossing the interstellar medium. Yet 3I Atlas arrives from a direction that optimizes its encounters with both Mars and Earth during observational windows that favor detailed scientific study. The thermal evolution of both objects as they respond to increasing solar flux reveals complementary stories of cosmic processing under extreme conditions. Comet D 2025. T1's brightness follows curves that correlate precisely with distance from our Sun, confirming that we're observing natural ice sublimation driven by electromagnetic radiation. The mathematical relationships work out perfectly, validating centuries of scientific understanding about how frozen volatiles respond to stellar energy. 3I Atlas maintains activity levels that suggest internal processes supplementing the thermal input from our star. These additional energy sources aren't dramatic enough to indicate obvious artificial origins, but they're consistent enough to keep researchers puzzling over what additional mechanisms might be operating within this interstellar wanderer. As we continue our gentle journey through this cosmic mystery, allow your mind to drift toward the fundamental question of what these visitors are made of. The atoms and molecules that compose 3I Atlas have traveled farther than any material substance we've ever encountered, carrying within their structure the chemical fingerprints of stellar processes that occurred around a distant sun billions of years ago. The spectroscopic observations reveal a composition that challenges our understanding of how matter behaves in the extreme environments of interstellar space. When the Very Large Telescope in Chile turned its powerful instruments toward 3I Atlas, it detected emission lines from elements that rarely appear in such concentrations in natural objects. The chromium and vanadium signatures we mentioned earlier represent just the beginning of this chemical puzzle. More intriguing still is what the spectrographs don't detect. Iron, which should accompany these refractory metals in predictable cosmic ratios, appears to be almost entirely absent. This selective presence of some elements while others remain mysteriously absent creates a compositional fingerprint unlike anything cataloged in our extensive databases of asteroids, comets, and meteorites from throughout the solar system. The organic compounds identified within 3I Atlas's expanding coma tell equally fascinating stories about the chemistry of distant stellar nurseries. Complex carbon-based molecules, including what appear to be aromatic hydrocarbons and nitrogen-bearing compounds, suggest that the building blocks of life may be far more common throughout the galaxy than we previously imagined. These molecular signatures represent direct samples of organic chemistry that occurred around another star, preserved in the deep freeze of interstellar space for millions of years. Meanwhile, Comet D 2025 T1 releases a completely different suite of chemicals as it responds to solar heating. Water vapor dominates its spectrum, accompanied by carbon monoxide, methanol, and the other molecular species we've learned to expect from objects born in our own solar system's outer reaches. The contrast with 3I Atlas couldn't be more striking. One visitor behaving exactly as theory predicts, the other operating according to rules we're still trying to understand. The isotopic analysis adds another layer of mystery to this chemical portrait. Different isotopes of the same element form through specific nuclear processes operating under extreme conditions in stellar cores. The ratios observed in 3I Atlas don't match any known stellar nucleosynthesis models, suggesting either formation in stellar environments, unlike anything we've studied directly, or post-formation processing through mechanisms that remain beyond our current theoretical understanding. Let your thoughts now wander to the incredible journey that brought these cosmic travelers to their current rendezvous with our Sun. The physics involved in crossing the vast emptiness between stellar systems speaks to forces and timescales that dwarf human experience. Yet the mathematical precision of their arrival suggests something more purposeful than random cosmic billiards. 3I Atlas has been in motion for potentially millions of years, maintaining its structural integrity while traversing distances so vast that light itself takes years to cross them. During this immense journey, the object has been bombarded by cosmic rays, high-energy particles streaming from distant galaxies that slowly alter surface chemistry and create new molecular compounds through radiation processing. Each cosmic ray impact has left its mark, creating a cumulative record of the radiation environment encountered during the long voyage between stars. The gravitational environment of our solar system began influencing 3I Atlas's trajectory long before it became visible to our telescopes. As the object approached from the constellation Lyra, it encountered the subtle but persistent gravitational pull of our Sun, gradually accelerating and changing course in ways that can be predicted with extraordinary mathematical precision. Every calculation confirms that this visitor is following the laws of celestial mechanics exactly as expected. Yet the timing of its arrival continues to puzzle researchers. Comet D2025T1 tells the complementary story of a much longer journey that began not in another stellar system, but in the frigid outer reaches of our own cosmic neighborhood. This magnificent object spent thousands of years slowly falling toward the Sun from the Oort cloud, a vast spherical shell of icy debris that extends roughly halfway to the nearest star. Gravitational perturbations from passing stars or molecular clouds eventually nudged it onto its current trajectory, beginning a decades-long plunge toward the inner solar system. The orbital mechanics of both objects create a natural timeline for their convergence that seems almost choreographed for maximum scientific impact. 3I Atlas will reach its closest approach to our Sun in mid-November, just as Comet D2025T1 makes its nearest pass to Earth. This timing provides unprecedented opportunities for comparative studies of how objects from very different origins respond to the same thermal and gravitational environment. The energy budgets involved in these journeys stagger the imagination when considered from first principles. 3I Atlas carries kinetic energy equivalent to millions of nuclear weapons, all derived from the gravitational interactions that ejected it from its birth system millions of years ago. This energy has been conserved across interstellar distances, neither created nor destroyed, but simply transferred from one form to another according to the fundamental conservation laws that govern all motion in the universe. As we settle deeper into this cosmic meditation, consider the remarkable human achievement represented by our ability to decode the messages carried by these ancient travelers. The light reaching our eyes and instruments tonight left these objects just minutes or hours ago, yet it carries information encoded during formation processes that occurred when the galaxy was significantly younger than it is today. The global network of telescopes tracking both visitors operates with a coordination that spans continents and time zones. As Earth rotates, different observatories come online to maintain continuous surveillance, ensuring that no significant changes in brightness, spectral characteristics, or structural evolution go unrecorded. This collaborative effort represents one of the most intensive observational campaigns in the history of astronomy. The Hubble Space Telescope has contributed high-resolution imagery that reveals details in both objects' coma structures invisible to ground-based instruments. The sharp, unblinking vision available above Earth's atmosphere allows astronomers to track changes in gas and dust distribution that occur over timescales of days or weeks, providing insights into the physical processes occurring as both visitors respond to increasing solar flux. The James Webb Space Telescope brings its unprecedented infrared capabilities to bear on this cosmic convergence, penetrating the dust and gas surrounding both objects to observe the underlying nucleus structures and identify molecular species invisible at optical wavelengths. The infrared spectrum reveals the thermal signatures of sublimating ices and the distinctive emission lines of organic compounds that would remain hidden to visible light observations. Ground-based facilities contribute their own unique capabilities to this coordinated campaign. The very large telescope's sophisticated spectrographs can split the light from both objects into thousands of individual wavelengths, creating detailed chemical fingerprints that reveal the atomic and molecular composition of materials being released into space. Each spectral line tells a story about nuclear processes, chemical bonding, and physical conditions that existed during formation billions of years ago. Radio telescopes maintain constant vigil for any electromagnetic emissions that might indicate artificial origins or active processes beyond simple thermal radiation. The silence remains complete across all monitored frequencies, supporting natural explanations while providing no evidence for the more exotic scenarios that capture public imagination. This electromagnetic quiet represents one of the most convincing arguments for conventional interpretations of both visitors. The amateur astronomy community plays a crucial role in this observational symphony, providing temporal coverage and geographic distribution that professional facilities cannot match. Dedicated observers using sophisticated equipment document brightness variations, tail development, and structural changes with a consistency and dedication that complements the detailed scientific studies conducted by major observatories. Allow your mind to drift now toward the elegant mathematics that governs the motion of these cosmic dancers. In the vast theater of space, where objects move according to laws that have remained unchanged since the formation of the galaxy, we find ourselves witnessing a performance of gravitational choreography that seems to transcend mere chance. The trajectory of 3I Atlas follows a hyperbolic path through our solar system, a mathematical curve that never closes upon itself, marking this visitor as forever unbound to our sun's gravitational embrace. This geometric signature tells us immediately that we're observing a true interstellar wanderer, an object that will make its singular passage through our cosmic neighborhood before returning to the darkness between stars, never to be seen again. Every calculation confirms that 3I Atlas moves according to the precise predictions of celestial mechanics, yet the timing of its arrival challenges our understanding of how random such encounters should be. The object approaches from a direction that creates optimal viewing geometries for Earth-based telescopes, passing close enough to Mars for detailed observations by our robotic emissaries while maintaining safe distances that pose no threat to any planet in our solar system. Comet D 2025 T1 traces its own mathematical poetry across the sky, following an extremely elongated ellipse that carries it from the frigid outer reaches beyond Neptune to within half an astronomical unit of our Sun. This orbital geometry speaks of a journey that began in the distant Oort cloud, where gravitational nudges from passing stars occasionally send these frozen relics tumbling toward the inner solar system after thousands of years of patient waiting. The precision required to coordinate such trajectories across the vast scales of space and time staggers the imagination. If we were to imagine these as guided missiles rather than natural objects, the computational requirements would exceed anything within human technological capability. The targeting accuracy demonstrated by 3I Atlas, arriving at precisely the moment when another spectacular visitor graces our skies, suggests either extraordinary coincidence or underlying mechanisms that operate according to principles we don't fully understand. The gravitational perturbations experienced by both objects as they navigate our solar system's complex force fields provide additional insights into their physical properties. The subtle changes in trajectory caused by planetary encounters reveal information about mass distribution and internal structure that no telescope could determine through direct observation. 3I Atlas responds to these gravitational influences exactly as predicted for a natural object of its estimated size and density. As we continue this peaceful journey through cosmic mysteries, let your thoughts turn to the profound implications of what we're witnessing. The light reaching our eyes tonight carries information that has been preserved across distances and time spans that challenge human comprehension, offering us glimpses into stellar processes that shaped the galaxy long before our sun began to shine. The spectroscopic fingerprints of 3I Atlas encode stories about nuclear fusion reactions that occurred in the core of a massive star billions of years ago. Each emission line corresponds to specific atomic transitions that occur when electrons absorb and emit photons of precise energies. These quantum mechanical processes operate according to physical laws so fundamental that they remain identical whether they occur in laboratory experiments on Earth or in the expanding atmosphere of an interstellar visitor racing past our sun. The isotopic ratios observed in both objects provide additional clues about their origins and evolutionary histories. Different isotopes of the same element form through distinct nuclear processes, creating atomic fingerprints that reveal the types of stars responsible for forging these materials and the specific conditions under which they were created. The patterns we observe tell stories of stellar death and rebirth, of cosmic recycling processes that have been operating since the first generations of stars began enriching the interstellar medium with heavy elements. The organic chemistry detected in 3I Atlas represents perhaps the most philosophically significant aspect of this cosmic encounter. The complex carbon-based molecules identified in its expanding coma formed around another star in environments that may have been more or less favorable for the emergence of life than the conditions that existed during our own solar system's formation. These compounds serve as chemical fossils, preserving information about prebiotic processes that occurred in stellar nurseries we'll never visit. The dust particles released by both objects carry their own messages about cosmic evolution and the distribution of solid materials throughout the galaxy. Each microscopic grain represents a sample of matter that condensed from gas clouds enriched by countless generations of dying stars. The size distributions and optical properties of these particles provide insights into the physical processes that create solid materials in different stellar environments. Temperature measurements reveal how both objects respond to the increasing intensity of solar radiation as they approach their closest encounters with our star. The thermal evolution follows predictable patterns based on the physics of ice sublimation and dust emission, yet subtle deviations in 3I Atlas's behavior continue to puzzle researchers who study the thermal properties of small solar system bodies. The magnetic field measurements attempted by several research groups have yielded tantalizing hints about the internal structure and evolutionary history of 3I Atlas. While the signals remain at the limits of detectability, they suggest magnetic properties that differ from typical asteroids and comets, potentially indicating either unusual composition or formation processes that created systematic rather than random field configurations. Let your awareness expand now to encompass the remarkable human enterprise dedicated to understanding these celestial visitors. Around our planet, a network of electronic eyes maintains constant vigilance, each contributing its unique capabilities to a collaborative effort that represents one of the most coordinated scientific campaigns in human history. The Atacama Large Millimeter Array in Chile turns its array of synchronized dishes toward both objects, observing at wavelengths where molecular emission lines create detailed chemical fingerprints invisible to optical telescopes. The radio signatures reveal the three-dimensional structure of gas clouds surrounding both nuclei, mapping the distribution of different molecular species as they respond to solar heating and radiation pressure. Space-based observatories provide perspectives impossible to achieve from Earth's surface, free from atmospheric interference and capable of observing wavelengths absorbed by our planet's atmosphere. The Spitzer Space Telescope contributes infrared observations that penetrate dust clouds to reveal underlying structures, while X-ray telescopes search for high-energy emissions that might indicate exotic physical processes beyond conventional sublimation and outgassing. The coordination required for this global campaign pushes international cooperation to new levels of sophistication. Telescope schedules must be synchronized across multiple time zones, data sharing protocols established for real-time collaboration, and observation priorities balanced among competing scientific objectives. The result is a level of coordination that demonstrates humanity's capacity for focused, collaborative investigation of phenomena that transcend national boundaries. Ground-based radar systems attempt to bounce signals off both objects, though the extreme distances involved make detection challenging, even for the most powerful planetary radar facilities. These active observations could potentially reveal surface textures, rotation states, and internal structures invisible to passive optical and infrared observations, providing crucial constraints on theoretical models of both objects' origins and evolution. The amateur astronomy community contributes observations that professional facilities cannot match in terms of temporal coverage and geographic distribution. Dedicated observers using sophisticated equipment provide continuous monitoring that captures rapid changes and transient events that might be missed by scheduled professional observations. Social media platforms serve as clearinghouses for real-time data sharing, creating distributed networks that enable rapid dissemination of discoveries and anomalies. Citizen science projects engage thousands of volunteers in analyzing observational data, identifying patterns and anomalies that might escape automated processing algorithms. The collective effort represents one of the largest coordinated responses to astronomical phenomena in human history, demonstrating how modern communication technologies can mobilize global expertise around focused research objectives. As your mind settles into the rhythm of this cosmic story, let yourself contemplate the beautiful physics unfolding as both visitors respond to our sun's increasing warmth. The thermal evolution of these objects reveals fundamental processes that have shaped the solar system for billions of years. Yet each visitor responds according to its own unique composition and history. Comet D 2025 T1 follows the textbook physics of ice sublimation with elegant precision. As solar radiation penetrates its surface layers, frozen volatiles transition directly from solid to gas phase, bypassing the liquid state entirely in the near vacuum of space. Different molecular species sublimate at different temperatures, creating a natural timeline of chemical revelation as the comet approaches closer to our star. First, carbon monoxide and nitrogen ices begin to vaporize at temperatures still far below freezing, followed by water ice, and finally, more refractory organic compounds as surface temperatures rise. This predictable cascade of sublimation creates the spectacular tale that stretches across our evening skies, a gossamer structure so tenuous that its density approaches laboratory vacuum conditions, yet visible across millions of kilometers due to the sheer volume of space it occupies. The tail points steadily away from our sun, shaped by radiation pressure and solar wind interactions according to physical laws so well understood that astronomers can predict its appearance months in advance. 3I Atlas tells a more complex thermal story that continues to puzzle researchers studying the physics of small solar system bodies. While the object clearly responds to solar heating through increased gas and dust production, the details of this response deviate subtly from standard models in ways that suggest either unusual composition or internal processes beyond simple ice sublimation. The thermal infrared emissions captured by space-based observatories reveal temperature distributions that follow predictable patterns for solar heating, yet embed subtle features that persist despite changing illumination conditions. The object appears to maintain internal temperatures that require energy inputs, supplementing the electromagnetic radiation received from our sun. These additional energy sources remain within the bounds of natural explanation, perhaps radioactive decay of trace isotopes or chemical reactions between different molecular species, but they create thermal signatures that distinguish 3I Atlas from typical comets. The dust production rates provide another window into the thermal processes occurring within both objects. As volatile ices sublimate, they carry embedded dust particles into space, creating the expanding coma that makes both visitors visible to our telescopes. The size distribution and optical properties of these microscopic fragments encode information about the original materials from which both objects formed, offering insights into conditions in stellar nurseries separated by vast distances of space and time. Polarimetry measurements reveal additional details about the dust grains being released, analyzing how they scatter and polarize sunlight to determine particle shapes, compositions, and size distributions. These observations provide crucial constraints on theoretical models of how solid materials condense from gas clouds in different stellar environments. Let your thoughts drift now toward the invisible forces that have shaped the journeys of these cosmic travelers. Gravity, that most fundamental of nature's influences, has been the silent choreographer, directing their paths across the galaxy for millions of years, writing their stories in the elegant mathematics of orbital mechanics. The gravitational environment of our solar system began influencing 3I Atlas long before it became visible to our instruments. As the object approached from interstellar space, it encountered the subtle but persistent pull of our Sun's gravity well, gradually accelerating and changing course according to the inverse square law that governs all gravitational interactions. The mathematical precision of this process allows astronomers to trace the visitor's path backward through space and time, revealing its trajectory through our local galactic neighborhood. Every planetary encounter adds its own gravitational signature to this cosmic story. As 3I Atlas passes within the sphere of influence of Jupiter or Mars, these massive bodies tug gently on the visitor, creating minute changes in velocity and direction that accumulate over time into measurable modifications of its trajectory. These perturbations provide valuable information about the object's mass and internal structure, revealing details about its composition and evolution that no telescope could determine through direct observation. The concept of gravitational memory emerges from these interactions, the way that every encounter with massive objects leaves permanent imprints on an object's motion through space. The current trajectory of 3I Atlas carries encoded information about every significant gravitational encounter it has experienced during its million-year journey, creating a kind of fossil record of its passage through the galaxy, written in the language of orbital mechanics. Comet D 2025. T1's gravitational story spans a much longer timeline, beginning with its formation in the outer reaches of our solar system billions of years ago. The weak gravitational binding that initially held it in the distant Oort cloud was eventually overcome by the accumulated influence of passing stars, molecular clouds, and the galactic gravitational field itself. These subtle perturbations, operating over thousands of years, gradually altered its orbit until it began the long fall toward our Sun that we witness today. The tidal forces experienced by both objects as they approach their closest solar encounters create additional gravitational effects that reveal information about their internal structure and composition. Just as our moon raises tides in Earth's oceans, the differential gravitational pull across each visitor's structure creates minute deformations that can be detected through careful analysis of brightness variations and spectroscopic changes. These tidal interactions provide crucial tests of theoretical models describing the internal structure of small solar system bodies. Solid, rocky objects respond differently to tidal stress than loosely bound collections of smaller fragments held together by weak gravitational forces. The observed responses of both visitors to these gentle but persistent forces help constrain our understanding of their formation processes and evolutionary histories. As we continue this meditative journey through the cosmos, allow yourself to marvel at the extraordinary fact that light itself serves as our translator for stories written in stellar nuclei billions of years ago. Every photon reaching our instruments tonight carries information encoded during nuclear fusion reactions that occurred when the galaxy was younger and very different from the structured spiral we observe today. The spectroscopic analysis of both objects reveals atomic fingerprints that speak directly to the nuclear physics operating in stellar cores during the final stages of massive star evolution. When stars 8 or more times the mass of our Sun exhaust their nuclear fuel, they undergo catastrophic collapse, followed by explosive expansion that forges heavy elements and scatters them throughout the surrounding interstellar medium. The specific isotopic ratios we observe in 3I Atlas encode information about these stellar death throes, revealing details about nuclear reaction networks that operated under conditions more extreme than anything humans have directly witnessed. The emission lines visible in the expanding comas of both visitors correspond to electronic transitions in atoms and molecules that absorb and emit photons of precise energies. These quantum mechanical processes operate according to physical laws so fundamental that they remain identical whether they occur in terrestrial laboratories or in the expanding atmosphere of an interstellar wanderer. The universality of these physical constants allows us to decode chemical compositions and physical conditions with confidence, knowing that the same atomic physics governs matter throughout the observable universe. The Doppler shifts measured in these spectral lines reveal the three-dimensional motion of gas and dust around both objects, mapping the velocity fields created by sublimation processes and radiation pressure effects. These measurements provide insights into the internal structure and rotation states of both visitors, revealing details about their spin rates, surface topology, and mass distribution that complement direct imaging observations. The polarization properties of light scattered by dust particles in both comas encode additional information about particle shapes, compositions, and size distributions. Linear polarization reveals details about particle geometry and surface roughness, while circular polarization can indicate magnetic field effects or unusual optical properties that might suggest exotic material compositions. The temporal evolution of spectroscopic signatures provides crucial insights into the physical processes occurring as both objects respond to changing solar illumination and gravitational environments. Brightness variations, spectral line, strength changes, and new molecular species appearing or disappearing create dynamic portraits of active physical and chemical processes occurring in real time as we observe them. The infrared excess emissions detected by sensitive thermal observations reveal information about dust production rates and particle size distributions invisible to optical wavelengths. These thermal signatures provide constraints on the internal heat sources and thermal properties that help distinguish between different theoretical models of how these objects formed and evolved. Allow your consciousness to drift now toward the beautiful precision that governs the motion of these cosmic visitors through our solar system. Like dancers following an ancient choreography, both objects move according to mathematical laws that have remained unchanged since the galaxy's formation. Their every step predictable, yet their convergence seemingly impossible. The rotation of 3I Atlas reveals itself through periodic variations in brightness as different portions of its irregular surface alternately face toward and away from our observing instruments. These light curves encode information about the object's shape, surface properties, and spin state, details that provide crucial insights into its formation history and the mechanical forces it has experienced during its long interstellar journey. Most small bodies in space tumble chaotically, their rotation states randomized by countless impacts and gravitational encounters accumulated over billions of years. The typical asteroid or comet displays erratic brightness changes that reflect this random tumbling motion, creating light curves that appear almost organic in their unpredictability. Yet 3I Atlas exhibits rotational characteristics that suggest either remarkable structural uniformity or systematic influences that have maintained stable spin dynamics despite the extreme environments encountered during its interstellar voyage. The period of rotation, approximately 7.3 hours for each complete spin cycle, falls within the range observed for similar-sized objects throughout the solar system. Yet, the consistency of this periodicity across months of observation indicates rotational stability rarely achieved by natural tumbling bodies. This stability becomes even more remarkable when considered against the disturbing influences that should gradually alter any object's spin state during close approach to our Sun. Comet D 2025 T1 displays more conventional rotational behavior, with brightness variations that clearly reflect the chaotic tumbling expected from a fragment ejected from the distant Oort cloud. The irregular light curve reveals an elongated, potato-shaped object spinning end over end every 12.7 hours, creating the brightness variations that allow astronomers to determine its basic physical properties through patient photometric monitoring. The non-gravitational forces acting on both objects as they release gas and dust create subtle but measurable changes in their trajectories that can be detected through precise astrometric measurements. When volatile materials sublimate from one side of a rotating nucleus more readily than the other, they create tiny rocket-like effects that gradually alter orbital parameters in ways that must be accounted for in long-term trajectory predictions. These non-gravitational accelerations provide valuable insights into the surface properties and internal structure of both visitors. The magnitude and direction of these effects depend on factors such as surface roughness, thermal conductivity, and the distribution of volatile materials across each object's surface, creating observable signatures that help constrain theoretical models of their composition and evolution. Let your mind settle now into contemplation of the exquisite molecular ballet occurring as both visitors respond to our Sun's increasing warmth. Each molecule escaping into space carries with it information encoded during formation processes that occurred in stellar nurseries separated by vast distances of time and space. The expanding coma surrounding 3I Atlas reveals a complex chemistry that speaks to formation conditions unlike anything found in our local cosmic environment. Water vapor, while present, plays a surprisingly minor role compared to more exotic species such as carbon dioxide, methanol, and various organic compounds. This composition suggests formation in stellar regions, where temperature and pressure conditions differed significantly from those that characterized our own solar system's birth. The production rates of different molecular species follow patterns that deviate subtly from standard sublimation models, creating chemical signatures that continue to puzzle researchers studying the physics of ice transitions in vacuum environments. While the overall behavior remains consistent with natural processes, the specific ratios and temporal evolution of gas release suggest either unusual bulk composition or surface processes that operate according to principles not fully captured by conventional cometry models. Spectroscopic observations reveal the three-dimensional structure of gas flows around both objects, mapping velocity fields created by sublimation pressure and radiation effects. These measurements provide insights into the surface, topography, and activity patterns that would be impossible to determine through direct imaging at such extreme distances. The organic molecules detected in 3I Atlas's expanding atmosphere represent some of the most intriguing aspects of this cosmic encounter. Complex carbon-based compounds, including aromatic hydrocarbons and nitrogen-bearing species, formed around a distant star and have been preserved in the deep freeze of interstellar space for millions of years. These molecules serve as direct samples of prebiotic chemistry that occurred in stellar environments we may never directly observe. Comet D 2025 T1 releases a completely different suite of molecules that reflects its formation in the cold outer regions of our own solar system. The familiar signatures of water vapor, carbon monoxide, and simple organic compounds create spectroscopic fingerprints that match theoretical predictions with satisfying precision, validating our understanding of how pristine materials from the Oort cloud respond to solar heating. The dust particles carried along with these expanding gas clouds provide additional information about the solid materials from which both objects formed. Microscopic analysis of the optical properties of these grains reveals size distributions, compositions, and structural characteristics that encode information about accretion processes operating in different stellar environments. The temporal evolution of both gas and dust production creates dynamic portraits of active sublimation processes occurring in real time as we observe them. Changes in production rates, the appearance of new molecular species, and variations in dust properties all contribute to our evolving understanding of how these ancient materials respond to the intense thermal and radiation environment near our Sun. As we continue this gentle exploration of cosmic mysteries, let your awareness expand to encompass the remarkable preservation of materials that have remained essentially unchanged for millions of years in the frigid environment of interstellar space. The internal structure of 3I Atlas represents a kind of cosmic time capsule, maintaining chemical and physical records of conditions that existed around another star when our own solar system was still forming. The layered structure implied by the sequential release of different volatile species suggests an onion-like internal architecture, with the most easily sublimated materials concentrated near the surface and more refractory compounds protected in the interior. This stratification could reflect either the original accretion sequence that formed the object billions of years ago or subsequent processing by cosmic radiation and thermal cycling during its interstellar journey. Laboratory studies of meteorites and interplanetary dust particles provide templates for understanding how such structures might form and evolve over cosmic time scales. The gradual modification of surface chemistry by cosmic ray bombardment, the slow penetration of radiation into subsurface layers, and the effects of repeated thermal cycling all contribute to creating complex internal architectures that preserve multiple epochs of chemical evolution. The strength and cohesion of 3I Atlas, as inferred from its survival of the extreme thermal gradients experienced during solar approach, suggest either unusually strong binding mechanisms or internal structures that distribute mechanical stress more effectively than typical rubble pile assemblages. This structural integrity becomes particularly significant when considered against the tidal forces and thermal expansion effects that should tend to fragment weakly bound objects. Theoretical models of interstellar ice evolution predict that complex chemical reactions should occur even at the extremely low temperatures of deep space, driven by the slow but persistent bombardment of high-energy cosmic rays. These processes could create new molecular species, alter isotopic ratios, and modify crystalline structures in ways that distinguish interstellar materials from objects that formed and remained within individual stellar systems. The preservation of organic compounds within 3I Atlas across millions of years of interstellar transit speaks to the remarkable stability of complex chemistry under the extreme conditions of deep space. The near absolute vacuum and ultra-low temperatures create ideal conditions for maintaining delicate molecular structures that would quickly decompose in more active environments. Comparison with Comet D 2025 T1 provides crucial insights into the differences between materials formed in our local stellar environment versus those that originated around distant stars. The contrasting chemical signatures, thermal responses, and physical properties of these two visitors create a natural laboratory for studying how stellar system characteristics influence the formation and evolution of small, solid bodies. The isotopic signatures preserved in both objects encode information about the nuclear processes that created their constituent elements in stellar cores billions of years ago. These atomic fingerprints provide direct links to the stellar generations that enriched the interstellar medium with heavy elements, creating the raw materials from which both rocky planets and biological molecules eventually formed. As your thoughts drift deeper into this cosmic meditation, consider the profound quietude that characterizes both of our celestial visitors. In an age where human technology fills the electromagnetic spectrum with constant chatter, these ancient wanderers move through space in complete radio silence, their only communications written in the ancient languages of light and gravity. The global network of radio telescopes maintains continuous surveillance across all frequencies where artificial signals might manifest. The Very Large Array in New Mexico, the upgraded Arecibo facilities, and radio observatories scattered across 6 continents all listen with electronic ears more sensitive than anything that existed just decades ago. Yet both 3I Atlas and Comet D 2025 T1 remain electromagnetically invisible beyond their natural thermal radiation and reflected sunlight. This radio silence speaks to the fundamental processes governing both objects. Natural bodies in space emit thermal radiation according to their temperature, reflect electromagnetic radiation according to their surface properties, and occasionally generate weak radio emissions through plasma interactions with the solar wind. But they produce none of the coherent signals, structured transmissions, or artificial modulations that would indicate technological origins or active electronic systems. The plasma environment surrounding both objects as they interact with the solar wind creates complex electromagnetic phenomena that operate according to well understood physical principles. Charged particles from our Sun encounter the expanding gas clouds around both visitors, creating bow shock structures and magnetic field distortions that can be detected by sensitive magnetometers aboard spacecraft throughout the solar system. These natural plasma interactions produce their own form of electromagnetic music, whistling radio waves, crackling static from magnetic field reconnection events, and the gentle hum of charged particles spiraling along field lines. Yet within this natural symphony, no artificial notes intrude to suggest purposes beyond the elegant physics of matter and energy interacting in vacuum. The search for coherent signals represents more than simple curiosity about potential artificial origins. Any genuine electromagnetic emissions would provide crucial information about internal processes, structural properties, or compositional characteristics invisible to optical and infrared observations. The absence of such signals, while supporting natural explanations, also eliminates potential diagnostic tools that might reveal hidden aspects of both objects' nature and evolution. Radar observations attempted by several facilities have yielded mixed results due to the extreme distances involved and the relatively small size of both targets. The signals that do return provide constraints on surface roughness and bulk density, though the data remain at the limits of current detection capabilities and require careful statistical analysis to extract meaningful scientific information. Let your awareness now expand to encompass the invisible forces that have shaped every aspect of these cosmic journeys. Gravity, that most fundamental and mysterious of nature's influences, has been the silent author of trajectories that span millions of years and billions of kilometers, writing stories in the elegant mathematics of orbital dynamics. The hyperbolic trajectory of 3I Atlas tells a tale of velocity so extreme that our Sun's gravitational embrace cannot capture this wanderer permanently. Every calculation confirms that this visitor will make its singular passage through our solar system before returning to the interstellar void, carrying with it whatever secrets it has gathered during its brief encounter with our cosmic neighborhood. The gravitational perturbations experienced during close approaches to massive planets provide valuable information about both objects' internal structure and mass distribution. As 3I Atlas passes within the gravitational sphere of influence of Jupiter or Mars, these encounters create minute changes in trajectory that accumulate into measurable modifications of orbital parameters over time. These gravitational interactions operate according to principles so fundamental that they allow astronomers to predict future positions with extraordinary accuracy months or years in advance. The mathematical precision underlying these calculations represents one of humanity's greatest intellectual achievements, the ability to describe and predict the motion of objects across cosmic distances using equations that fit on a single page. The concept of gravitational memory emerges from these interactions, the way that every encounter with massive objects leaves permanent imprints on orbital motion. The current trajectory of 3I Atlas encodes information about every significant gravitational influence it has experienced during its million-year journey, creating a fossil record of its passage through the galaxy written in the language of celestial mechanics. Tidal forces acting on both objects during their closest solar approaches create additional gravitational effects that reveal information about internal structure and composition. The differential gravitational pull across each visitor's extended body creates subtle deformations that can be detected through careful analysis of brightness variations and rotational dynamics. These tidal interactions provide crucial tests of theoretical models describing how small solar system bodies respond to external stress. Solid, monolithic objects react differently to tidal forces than loosely bound collections of smaller fragments held together by weak gravitational attraction. The observed responses help constrain our understanding of formation processes and evolutionary histories. The orbital resonances that occasionally develop between small bodies and massive planets can create complex dynamical behaviors that persist across geological timescales. While neither visitor appears to be caught in such resonances during this passage, the mathematical frameworks developed to understand these phenomena provide tools for analyzing the long-term evolution of populations of interstellar objects. As we drift further into this contemplative journey, allow yourself to appreciate how these visitors serve as natural laboratories for studying physical processes under conditions impossible to replicate in terrestrial facilities. The extreme environments they create and traverse reveal physics operating at the boundaries of our theoretical understanding. The vacuum conditions surrounding both objects approach absolute perfection, with particle densities millions of times lower than the best laboratory vacuums achievable on Earth. In these conditions, familiar processes like sublimation, chemical reactions, and particle interactions operate according to principles that can only be studied through astronomical observations of natural phenomena. The temperature gradients experienced during solar approach create thermal stress environments that test the mechanical properties of ancient materials formed around distant stars. Surface temperatures that vary from near absolute zero to hundreds of degrees Kelvin within hours create expansion and contraction cycles that reveal information about structural integrity, composition, and internal architecture. The radiation environment encountered by both objects includes not only electromagnetic radiation from our Sun, but also the continuous bombardment of cosmic rays. High-energy particles accelerated to near light speed by supernova explosions and other violent cosmic phenomena. This radiation processing slowly modifies surface chemistry and creates new molecular species through nuclear interactions impossible to achieve in earthbound laboratories. The plasma physics occurring as both objects interact with the solar wind creates conditions where charged particles, magnetic fields, and electromagnetic radiation interact in ways that illuminate fundamental processes operating throughout the universe. These natural experiments in magnetohydrodynamics provide insights into phenomena ranging from stellar atmospheres to galactic magnetic field structures. The dust dynamics observed as both objects release microscopic particles into space reveal gravitational, electromagnetic, and radiation pressure effects operating simultaneously across multiple scales. Individual grains experience forces that depend on their size, shape, composition, and electrical charge, creating complex particle trajectories that map the local force environment with extraordinary precision. Spectroscopic observations of excited atoms and molecules in the expanding comas provide access to quantum mechanical processes operating under conditions of extreme dilution and isolation. Electronic transitions that might be obscured by collisional effects in denser environments become clearly visible, allowing detailed studies of atomic and molecular physics under conditions approaching the theoretical ideal of isolated quantum systems. The chemical reactions occurring as sublimated materials mix and interact in the near vacuum environment around both objects create opportunities to study reaction kinetics and thermodynamics under conditions where collision frequencies are so low that individual molecular encounters can have measurable effects on overall chemical evolution. Let your mind drift now toward the extraordinary spans of time that connect these visitors to events that shaped our galaxy long before Earth existed. The materials composing both objects carry within their atomic structure memories of stellar processes that operated when the universe was younger and fundamentally different from the cosmos we observe today. The formation of 3I Atlas occurred during an epoch when stellar birth rates throughout the galaxy were significantly higher than current levels, creating stellar nurseries rich with the energetic phenomena associated with young, massive stars. The chemical signatures preserved in its structure reflect this more active galactic environment, where supernova explosions occurred more frequently, and stellar winds were more intense than anything observed in our current cosmic neighborhood. The journey time required for 3I Atlas to travel from its birth system to our solar system spans millions of years, a duration that encompasses the entire evolutionary history of complex life on Earth. During this immense voyage, our planet transformed from a world dominated by simple microorganisms to the biologically complex environment we know today, while this ancient wanderer maintained its structural integrity across interstellar distances. Comet D-2025, T1, connects us to a different temporal scale, representing materials that condensed in the outer regions of our own solar system during its formation 4.6 billion years ago. These substances have remained essentially unchanged in the deep freeze of the Oort cloud, preserving direct samples of the primordial materials from which Earth and the other terrestrial planets eventually formed. The contrast between these temporal scales illuminates the different ways that cosmic time operates across various environments. While Earth has experienced billions of years of geological and biological evolution, the pristine ices of the Oort cloud have remained virtually unchanged since the solar system's birth. Meanwhile, 3I Atlas has spent millions of years crossing the relatively static environment of interstellar space, where temperatures approach absolute zero and change occurs only through the slow accumulation of cosmic ray interactions. The isotopic decay processes operating within both objects provide internal clocks that encode information about their ages and thermal histories. Radioactive elements incorporated during formation gradually transform into stable isotopes according to precisely known decay rates, creating atomic calendars that reveal when these materials first condensed from stellar atmospheres billions of years ago. The cosmic ray exposure ages recorded in surface materials tell additional stories about the duration of interstellar transit and the radiation environments encountered during these epic journeys. Each high-energy particle collision leaves microscopic scars in crystal structures that accumulate over time, creating records of radiation exposure that can be decoded to reconstruct the history of both objects' passages through space. The preservation of organic molecules across such enormous timescales speaks to the remarkable stability of complex chemistry under the extreme conditions of deep space, where the near-vacuum environment and ultra-low temperatures create ideal conditions for maintaining delicate molecular structures that would rapidly decompose in more active environments. As we continue this peaceful exploration of celestial mechanics, allow your awareness to encompass the beautiful fluid dynamics occurring as both visitors release microscopic particles into the solar wind. The interaction between matter and energy creates gossamer structures that span millions of kilometers, yet remain so tenuous that their density approaches the theoretical perfection of absolute vacuum. The dust production mechanisms operating in both objects follow fundamentally different physical principles that reflect their contrasting origins and compositions. Comet D 2025 T1 releases particles through the familiar process of drag entrainment, where sublimating gases carry embedded dust grains along as they expand into vacuum. This process creates the spectacular visible tail that stretches across our evening skies, a structure so extended that it appears to bridge vast distances despite being composed of particles no larger than smoke. 3I Atlas exhibits more complex dust emission patterns that suggest either unusual surface properties or emission processes that supplement simple drag entrainment through additional mechanisms. The particle size distributions and optical properties observed in its expanding coma indicate dust production rates and characteristics that deviate subtly from standard models, creating signatures that continue to intrigue researchers studying the physics of small body evolution. The radiation pressure effects acting on dust particles create natural sorting mechanisms that separate grains according to their size, composition, and optical properties. Smaller particles experience stronger acceleration away from the sun, while larger fragments follow trajectories more strongly influenced by gravitational forces. This natural fractionation creates distinct dust populations with different dynamical behaviors and observable characteristics. The plasma interactions occurring as dust particles encounter the solar wind add additional complexity to this hydrodynamic environment. Charged particles from our sun can alter the electrical properties of dust grains, creating electromagnetic forces that influence particle trajectories in ways that depend on grain composition, size, and surface properties. These effects create subtle but measurable modifications to dust tail geometry that provide diagnostic information about particle characteristics. The temporal evolution of dust production in both objects reveals dynamic processes occurring in real time as we observe them. Changes in production rates, the appearance of new particle populations, and variations in optical properties all contribute to our evolving understanding of how these ancient materials respond to the intense radiation environment near our sun. Polarimetry measurements of scattered sunlight provide additional constraints on dust particle shapes, compositions, and surface textures invisible to conventional photometric observations. The degree and orientation of linear polarization encode information about particle geometry and optical properties that help distinguish between different theoretical models of dust formation and evolution processes. The long-term fate of particles released by both objects depends on complex interactions between solar radiation pressure, planetary gravitational perturbations, and electromagnetic forces that operate over timescales ranging from days to millions of years. Some particles will eventually impact planetary surfaces, others will be blown out of the solar system entirely, and still others will settle into quasi-stable orbits that allow them to circulate through the inner solar system for extended periods. Let your consciousness now attune itself to the subtle vibrations and oscillations that characterize both visitors as they respond to the complex force environment of our solar system. These cosmic frequencies, operating across scales from molecular vibrations to orbital resonances, create a symphony of physical processes that reveals fundamental information about structure, composition, and evolutionary history. The rotational frequencies of both objects create periodic variations in their observable properties that serve as windows into their internal architecture and mass distribution. The precise measurement of these rotation periods, combined with detailed analysis of brightness variations, allows astronomers to constrain theoretical models of shape, density, and structural coherence that would be impossible to determine through direct imaging at such extreme distances. 3I Atlas exhibits rotational characteristics that suggest either remarkable structural uniformity or systematic influences that maintain stable spin dynamics despite the extreme thermal and gravitational environments encountered during its solar approach. This rotational stability becomes particularly significant when considered against the asymmetric outgassing forces that should gradually alter spin states through rocket-like effects operating over observational timescales. The vibrational modes potentially excited within both objects by tidal forces and thermal gradients operate at frequencies determined by their elastic properties and internal structure. While these oscillations remain below current detection thresholds, theoretical models predict that sensitive future observations might reveal vibrational signatures that provide direct information about internal composition and mechanical properties. The magnetic field oscillations potentially generated by plasma interactions in the vicinity of both objects could create electromagnetic signatures at specific frequencies related to the local plasma environment and magnetic field strength. The search for such signals represents an active area of research that could provide unique insights into the plasma physics operating around small solar system bodies. The chemical reaction rates occurring in the expanding comas of both visitors operate according to kinetic principles that depend on temperature, density, and radiation flux in ways that create natural frequency responses to changing solar illumination. These chemical oscillations, while subtle, leave observable signatures in spectroscopic data that reveal information about reaction mechanisms and molecular interaction rates. The gravitational frequency response of both objects to periodic perturbations from planetary encounters could potentially reveal information about internal structure and elasticity through the analysis of long-term orbital evolution. While these effects operate over timescales much longer than current observational campaigns, they represent important theoretical frameworks for understanding how small bodies respond to external gravitational influences. The resonance phenomena that occasionally develop between orbital frequencies and rotational periods can create complex dynamical behaviors that persist across extended time periods. The search for such resonances in the motion of both visitors provides opportunities to test theoretical models of celestial mechanics under conditions that combine gravitational, thermal, and electromagnetic influences. As we drift deeper into this meditative exploration of cosmic phenomena, allow your thoughts to descend to the most fundamental level of reality, the quantum mechanical processes that govern the behavior of atoms and molecules within these ancient travelers. At scales smaller than anything directly visible, quantum effects orchestrate the chemical and physical transformations we observe unfolding across millions of kilometers of space. The quantum mechanical tunneling effects operating within both objects enable chemical reactions to proceed even at the extremely low temperatures encountered during interstellar transit. Normally, molecular transformations require sufficient thermal energy to overcome activation barriers, the energy hills that separate reactant molecules from their transformation products. However, quantum mechanics allows particles to tunnel through these barriers even when they lack the classical energy needed to surmount them, enabling slow chemical evolution to continue throughout the million-year journey between stars. The electronic transitions responsible for the spectroscopic signatures we observe operate according to quantum selection rules that determine which atomic and molecular states can participate in photon absorption and emission processes. These quantum mechanical constraints create the distinctive fingerprints that allow us to identify specific chemical species and determine their physical conditions even across the vast distances separating us from these cosmic visitors. The magnetic properties potentially present in both objects emerge from quantum mechanical phenomena, particularly the intrinsic angular momentum properties of electrons and atomic nuclei known as spin. These quantum spins interact with each other and with external magnetic fields according to principles that govern everything from the magnetic signatures detected by sensitive instruments to the spin-orbit coupling effects that influence spectroscopic line shapes and intensities. The quantum coherence effects that may operate within the crystalline structures of both objects could provide mechanisms for preserving complex molecular architectures across the extreme time and distance scales of interstellar travel. Certain quantum states exhibit remarkable resistance to environmental disturbance when properly isolated from decoherent sources, potentially allowing delicate chemical structures to maintain their organization throughout journeys that span geological time periods. The zero-point energy present in all quantum mechanical systems provides a fundamental energy floor that prevents absolute thermal equilibrium even at temperatures approaching absolute zero. This quantum mechanical energy contributes to the vibrational motion of atoms within crystal structures and may influence chemical reaction rates and molecular stability under the extreme conditions encountered during interstellar transit. The wave-particle duality fundamental to quantum mechanics manifests in the behavior of both electromagnetic radiation interacting with these objects and the matter waves associated with atomic and molecular motion. These quantum mechanical aspects influence everything from the absorption and scattering of light to the tunneling rates that enable chemical transformations at temperatures where classical physics would predict complete chemical inactivity. The quantum entanglement phenomena that might exist within the complex molecular structures of both objects could create correlations between distant parts of each system that influence their collective response to external perturbations, though such effects remain at the limits of current theoretical understanding and observational capability. Let your consciousness now expand to encompass the magnificent gravitational dance occurring as both visitors navigate through the complex force environment created by our Sun and planets. This celestial choreography operates according to mathematical principles that have remained unchanged since the galaxy's formation, yet create trajectories so precise they seem almost purposeful in their elegance. The gravitational sphere of influence of each major planet creates distinct dynamical regions through which both objects pass during their solar encounters. Jupiter's immense mass dominates the outer solar system, creating gravitational perturbations that subtly alter the trajectories of passing objects in ways that accumulate over time into measurable orbital changes. The precise timing and geometry of these encounters determine whether visitors receive energy boosts that accelerate their departure or experience deceleration effects that could potentially capture them into bound solar orbits. Mars provides a particularly significant gravitational benchmark for 3I Atlas, which will pass within approximately 35 million kilometers of the red planet during its November approach. This encounter offers unprecedented opportunities for close-range observations using the sophisticated instruments aboard our Martian orbiters, potentially revealing structural details and compositional characteristics invisible from Earth-based telescopes. The tidal forces generated by our Sun's gravity create differential accelerations across the extended bodies of both visitors, causing subtle deformations that provide insights into their internal structure and mechanical properties. These tidal interactions operate according to the same physical principles that raise ocean tides on Earth, but at magnitudes determined by the extreme gravitational gradient present near our star. The gravitational focusing effects that concentrate both visitors toward the inner solar system create natural opportunities for detailed observation that might not occur again for millions of years. The mathematical precision underlying these encounters demonstrates the predictive power of celestial mechanics while highlighting the remarkable coincidence of timing that brings both objects into optimal viewing positions simultaneously. The three-body gravitational interactions occurring when both visitors, the Sun, and various planets align in specific geometric configurations create complex dynamical effects that test the limits of our theoretical understanding. These multi-body gravitational problems generally lack analytical solutions, requiring sophisticated numerical integration techniques to predict long-term orbital evolution with acceptable accuracy. The gravitational memory effects encoded in the current trajectories of both objects carry information about every significant mass encounter experienced during their respective journeys. For 3I Atlas, this gravitational history extends back millions of years to include encounters with stars and molecular clouds throughout its passage across the galaxy, creating a fossil record of local galactic structure written in the mathematics of orbital mechanics. The conservation laws governing gravitational interactions ensure that energy and angular momentum remain constant throughout these encounters, creating constraints that limit possible orbital outcomes and enable precise predictions of future positions. These fundamental conservation principles provide the mathematical foundation for all trajectory calculations and long-term dynamical studies of small solar system bodies. As we continue this gentle journey through cosmic physics, let your mind settle into contemplation of the beautiful energy transformations occurring as both visitors respond to our sun's increasing warmth. The thermodynamic processes unfolding across millions of cubic kilometers of space reveal fundamental principles that govern the behavior of matter and energy throughout the universe. The heat capacity and thermal conductivity properties of both objects determine how efficiently they absorb and redistribute solar energy as they approach closer to our star. These thermal parameters depend on factors such as composition, porosity, and internal structure in ways that create observable signatures in temperature distributions and sublimation patterns that can be detected through infrared observations. The phase transitions occurring as different molecular species reach their sublimation temperatures create distinct thermodynamic signatures that reveal information about the bulk composition and layered structure of both visitors. Water ice, carbon dioxide, carbon monoxide, and various organic compounds each transition from solid to gas phase at characteristic temperatures, creating natural timelines of chemical revelation that unfold as solar heating penetrates deeper into each object's interior. The latent heat effects associated with these phase transitions absorb significant amounts of thermal energy without producing corresponding temperature increases, creating temperature plateaus and thermal buffering effects that influence the overall energy balance of both objects. These thermodynamic processes help regulate surface temperatures and control the rates at which volatile materials are released into space. The convective and conductive heat transfer mechanisms operating within both objects create temperature gradients that drive internal circulation patterns and influence the distribution of thermal energy throughout their structures. While convection remains minimal due to the extremely low densities involved, conductive heat transfer through solid frameworks provides the primary mechanism for thermal equilibration over time scales, ranging from hours to years. The radiative energy balance between absorbed solar radiation and thermal emission to space determines the steady-state temperatures achieved by both objects at different solar distances. This energy balance follows Stefan Boltzmann principles that relate temperature to the fourth power of thermal emission rates, creating nonlinear responses to changing solar illumination that influence both surface activity and internal heating patterns. The thermodynamic efficiency of sublimation processes determines what fraction of absorbed solar energy converts into kinetic energy of escaping gas molecules versus thermal energy that raises internal temperatures. These efficiency factors depend on surface properties, molecular binding energies, and local pressure conditions in ways that create distinctive thermal signatures for different compositional scenarios. The entropy changes associated with phase transitions and chemical reactions create thermodynamic driving forces that influence the direction and rate of ongoing physical and chemical transformations within both objects, contributing to the evolution of their observable properties as they respond to changing thermal environments during their solar encounters. Let your thoughts drift now toward the microscopic crystalline structures preserved within both visitors, tiny mineral archives that have maintained their atomic arrangements across spans of time that encompass the entire history of complex life on Earth. These crystalline matrices serve as repositories of information about stellar processes that operated when the galaxy was younger and very different from the structured spiral we observe today. The mineral phases identified through spectroscopic analysis of both objects reveal formation conditions that speak to the diverse environments present in stellar nurseries, separated by vast distances of space and time. Olivine, pyroxene, and other silicate minerals create distinctive absorption features that encode information about temperature, pressure, and chemical activity during the condensation processes that first assembled these materials from stellar atmospheres billions of years ago. The grain boundary structures within these crystalline materials preserve additional information about thermal histories and mechanical stress events experienced during formation and subsequent evolution. Defects, dislocations, and chemical gradients within individual crystal domains create microscopic records of the physical and chemical processes that shaped these materials over geological timescales. 3I Atlas exhibits mineral signatures that suggest formation in stellar environments, characterized by different temperature and pressure regimes than those that characterized our own solar system's birth. The relative abundances of different crystalline phases and their chemical compositions indicate condensation from gas clouds enriched by stellar nucleosynthesis processes that operated under conditions more extreme than anything observed in our local cosmic environment. The cosmic ray damage tracks preserved in crystal structures provide additional chronological information about the duration and intensity of radiation exposure during interstellar transit. High-energy particles create distinctive microscopic scars in mineral lattices that accumulate over time, creating records of radiation environments that can be decoded to reconstruct exposure histories spanning millions of years. Comet D 2025 T1 displays mineral characteristics typical of materials that condensed in the outer regions of our own solar nebula, with crystal structures and compositions that match theoretical predictions for formation in the cold, hydrogen-rich environment that characterized the early solar system's periphery. These familiar signatures provide crucial baselines for comparison with the more exotic mineralogy observed in our interstellar visitor. The preservation of original crystalline structures across such enormous time spans speaks to the remarkable stability of solid matter under the extreme conditions of deep space, where temperatures approach absolute zero and chemical reactions proceed at rates so slow that atomic arrangements can remain essentially unchanged for geological ages. The isotopic compositions trapped within crystal lattices encode additional information about the nuclear processes that created these elements in stellar cores billions of years ago. These atomic fingerprints provide direct connections to the stellar generations that enriched the interstellar medium with heavy elements, creating the raw materials from which both rocky planets and organic molecules eventually formed throughout the galaxy. As we continue this peaceful exploration of cosmic processes, allow your awareness to encompass the beautiful fluid dynamics occurring as both visitors interact with the stream of charged particles flowing outward from our Sun. The solar wind creates a dynamic plasma environment that sculpts the expanding gas clouds around both objects according to principles that govern magneto-hydrodynamic phenomena throughout the universe. The bow shock structures that develop upstream of both objects represent locations where the supersonic solar wind encounters obstacles created by their expanding comas, forcing the plasma flow to decelerate and change direction according to magnetohydrodynamic principles. These shock formations create distinctive signatures in plasma density, temperature, and magnetic field strength that can be detected by sensitive instruments aboard spacecraft throughout the solar system. The magnetic field draping effects that occur as solar wind field lines encounter the partially ionized gases surrounding both visitors, create complex magnetic geometries that channel charged particle flows and influence the acceleration of ions away from each object. These field configurations operate according to magnetic reconnection principles that govern plasma behavior in environments ranging from planetary magnetospheres to stellar corona. The charge exchange reactions occurring when high-energy solar wind protons collide with neutral atoms in both expanding comas create distinctive X-ray emissions that provide diagnostic information about gas densities, flow velocities, and chemical compositions invisible to observations at other wavelengths. These collision processes operate according to atomic physics principles that remain identical whether they occur near comets or in the outer atmospheres of planets. The plasma instabilities that develop in the interaction regions downstream of both objects create turbulent mixing processes that accelerate the dispersion of coma materials into the surrounding solar wind flow. These instabilities operate according to fluid dynamic principles that govern mixing processes throughout the universe, from stellar atmospheres to galactic plasma flows. The ion acceleration mechanisms operating in these plasma interaction regions can accelerate charged particles to energies significantly exceeding their initial thermal velocities, creating suprathermal particle populations that contribute to the overall energy balance of both expanding comas. These acceleration processes provide natural laboratories for studying plasma physics phenomena that operate on scales ranging from laboratory experiments to astrophysical environments. The magnetic field fluctuations generated by these plasma interactions create electromagnetic waves that propagate through the solar wind at characteristic frequencies related to ion gyration rates and plasma wave dispersion relations. The detection and analysis of these wave modes provide additional diagnostic tools for understanding the physical conditions and chemical compositions present in both interaction regions. The temporal evolution of these plasma interactions creates dynamic portraits of magnetohydrodynamic processes occurring in real time as both objects respond to changing solar wind conditions and their own evolving gas production rates during their approaches toward maximum solar heating. Let your consciousness now expand to contemplate the profound philosophical implications of witnessing these cosmic travelers in our night sky. The presence of 3I Atlas, carrying materials forged around a distant star, fundamentally challenges our understanding of isolation and uniqueness, revealing instead a universe where matter and perhaps even the building blocks of life flow freely between stellar systems across spans of space and time that dwarf human experience. The realization that we are observing actual samples of matter from another stellar system transforms our relationship with the cosmos from one of distant observation to direct physical contact. The atoms and molecules released by 3I Atlas into our solar system will eventually become incorporated into the interplanetary medium, potentially reaching Earth's atmosphere and joining the chemical inventory of our own planet. We are not merely observing alien materials, we are being visited by them in the most literal sense possible. The organic compounds detected in 3I Atlas's expanding coma carry implications that extend far beyond simple chemical curiosity. These complex carbon-based molecules formed around another star in environments that may have been more or less favorable for the emergence of life than the conditions that characterized our own solar system's birth. Their preservation across millions of years of interstellar transit suggests that the chemistry necessary for biological processes may be far more common throughout the galaxy than our Earth-centered perspective has traditionally assumed. The question of panspermia, the hypothesis that life's building blocks are distributed throughout the universe by cosmic processes, gains new relevance when considered in light of 3I Atlas's organic chemistry. If complex prebiotic molecules can survive interstellar journeys and potentially seed new worlds with the molecular tools necessary for biological evolution, then life itself may represent a galactic phenomenon rather than a terrestrial accident. The temporal perspective imposed by contemplating 3I Atlas's million-year journey places all human history within a cosmic context that is simultaneously humbling and inspiring. The entire development of human civilization, from the emergence of agriculture to the current space age, represents just the briefest moment in the timeline of this object's passage across the galaxy. Yet during this brief interval, we have developed the technological capability to detect, track, and analyze this ancient wanderer with extraordinary precision. The mathematical elegance underlying the orbital mechanics that govern both visitors reveals a universe that operates according to comprehensible physical laws, despite the vast scales of space and time involved. The ability to predict future positions and calculate past trajectories with extraordinary accuracy demonstrates the power of human reason to decode the fundamental principles that govern cosmic phenomena. The collaborative international effort required to study both objects represents one of humanity's finest expressions of curiosity-driven cooperation, transcending political boundaries and cultural differences in service of our common desire to understand the universe that gave us birth. This scientific collaboration provides a template for how our species might approach other challenges that require coordination across traditional divisions. The preservation of ancient materials across cosmic timescales suggests that information can be maintained and transmitted across the universe through physical processes operating over durations that exceed the lifespan of individual stars, planets, and, potentially, even entire civilizations. We are reading messages written in the language of chemistry and physics by stellar processes that operated before our sun began to shine. As we approach the conclusion of our cosmic meditation, let your mind embrace the beautiful symphony of electromagnetic radiation that connects us to these ancient travelers across the vast emptiness of space. Every wavelength of light carries its own unique information about physical processes, chemical compositions, and thermal conditions that would remain forever hidden without the remarkable human achievement of spectroscopic analysis. The visible light reflected by both objects tells stories about surface compositions, particle size distributions, and scattering properties that encode information about formation environments and evolutionary processes operating over cosmic time scales. The subtle color variations observed as different regions rotate into and out of view reveal heterogeneous surface properties that speak to complex histories of accretion, differentiation, and space weathering processes. The infrared thermal emissions captured by sensitive detectors reveal the temperature distributions and thermal properties that govern how both objects respond to solar heating. These thermal signatures follow predictable patterns based on distance from our Sun and surface characteristics, yet embed subtle features that continue to provide insights into internal structure, composition, and the physical processes occurring as ancient ices transition from solid to gas phase. The ultraviolet fluorescence observed when solar radiation excites atoms and molecules in both expanding comas creates distinctive emission line spectra that serve as chemical fingerprints for identifying specific atomic and molecular species. These fluorescence processes operate according to quantum mechanical principles that remain identical throughout the universe, allowing us to decode compositions and physical conditions with confidence despite the enormous distances involved. The radio wavelength observations conducted by sensitive interferometric arrays search for any electromagnetic signatures that might indicate processes beyond simple thermal emission and molecular fluorescence. The silence observed across all monitored frequencies provides crucial constraints on theoretical models, while eliminating certain categories of exotic explanations for the unusual characteristics observed in 3I Atlas. The polarization properties of scattered and emitted radiation encode additional information about magnetic fields, particle orientations, and scattering geometries that remain invisible to conventional photometric observations. These polarimetric signatures provide unique diagnostic capabilities for studying dust particle properties, magnetic field configurations, and the three-dimensional structure of gas and dust distributions around both objects. The temporal variations observed across all wavelengths create dynamic portraits of evolving physical and chemical processes occurring in real time as we observe them. Changes in brightness, spectral line intensities, polarization characteristics, and thermal emissions all contribute to our developing understanding of how these ancient materials respond to the intense radiation environment near our Sun. The integration of observations across the entire electromagnetic spectrum creates comprehensive portraits of both visitors that would be impossible to achieve using any single wavelength range, demonstrating the power of multi-wavelength astronomy to reveal phenomena that remain hidden to observations limited to narrow spectral windows. Let your thoughts now turn toward the lasting impact of this remarkable cosmic convergence on our understanding of the universe and our place within it. The arrival of 3I Atlas and its spectacular companion has created opportunities for scientific discovery that extend far beyond the immediate questions raised by their unusual characteristics and unprecedented timing. The analytical techniques developed for studying these visitors have pushed astronomical instrumentation and data processing capabilities to new levels of sophistication, creating technological advances that will benefit all areas of astronomical research for decades to come. The coordination protocols established for rapid response observations have demonstrated humanity's capacity for focused, collaborative investigation of phenomena that transcend national boundaries and traditional scientific disciplines. The theoretical frameworks developed for understanding interstellar objects and their interactions with planetary systems provide tools that will prove essential for interpreting future encounters with visitors from other stellar systems. The statistical models, refined through analysis of arrival rates and observational selection effects, create foundations for understanding the population characteristics and frequency distributions of interstellar wanderers throughout our local galactic neighborhood. The educational impact of this cosmic convergence has engaged millions of people worldwide in direct participation in scientific discovery, demonstrating how modern communication technologies can mobilize global curiosity and create communities of citizen scientists contributing to our understanding of cosmic phenomena. This public engagement represents a crucial investment in scientific literacy and appreciation for the methods and achievements of empirical investigation. The philosophical implications raised by direct encounter with materials from another stellar system will continue influencing human thought about our cosmic significance, our relationship with the broader universe, and the potential prevalence of life-supporting chemistry throughout the galaxy. These questions extend beyond astronomy into realms of meaning and purpose that touch the deepest aspects of human consciousness and cultural development. The preservation of detailed observational records creates permanent archives that will enable future researchers to extract additional insights using analytical techniques not yet developed and theoretical frameworks not yet conceived. The comprehensive documentation of this cosmic encounter ensures that its scientific value will continue growing as human knowledge and capability advance. The international cooperation demonstrated throughout this observational campaign provides templates for addressing other challenges that require coordination across traditional divisions, suggesting pathways for collaborative approaches to global problems that transcend scientific research. The success of this cooperative effort demonstrates what becomes possible when curiosity and wonder unite human efforts toward common goals. The methodological advances achieved through studying potentially unique phenomena create new capabilities for distinguishing between conventional and extraordinary explanations for astronomical observations, providing tools that will prove crucial for evaluating future discoveries that challenge established theoretical frameworks. As our gentle journey through this cosmic story draws to its peaceful conclusion, let yourself rest in the profound realization that we have witnessed something truly extraordinary, a convergence of ancient travelers that has connected us directly to the deep history of our galaxy, while opening windows into processes that operate on scales of space and time. That humble human experience yet inspire our highest aspirations for understanding. The dance of 3I Atlas and Comet D 2025 T1 through our solar system represents more than astronomical phenomena to be cataloged and analyzed. It embodies the fundamental interconnectedness that links every atom in our bodies to nuclear processes that operated in stellar cores billions of years ago, that connects every breath we take to the cosmic recycling processes that have been enriching the interstellar medium since the first generations of stars began forging heavy elements from primordial hydrogen. The organic molecules carried by 3I Atlas from its distant birth system speak to chemical processes that may be operating throughout the galaxy, creating and preserving the molecular building blocks necessary for life wherever suitable conditions persist for sufficient durations. We are not alone in the universe, not because we have detected signals from technological civilizations, but because we have discovered that the chemistry of life extends far beyond our solar system, distributed through space by processes that operate on cosmic scales. The preservation of information across such enormous spans of space and time suggests that the universe operates as a vast communications network, where physical processes encode and transmit messages in languages written in the fundamental properties of matter and energy. We have learned to read some of these messages through the remarkable human achievement of scientific investigation. Yet we have surely decoded only the first words of conversations that span the entire history of cosmic evolution. The collaborative human effort required to study these visitors demonstrates our species' capacity for cooperation in service of understanding, transcending the divisions that too often separate us in earthly affairs. The global network of observers, the sharing of data across political boundaries, and the coordination of resources represent some of our finest expressions of curiosity-driven collaboration. As both visitors continue their journeys, 3II Atlas departing forever for the interstellar void, Comet D 2025 T1 beginning its slow retreat toward the outer solar system, they carry with them subtle alterations in their chemistry and structure that record their passage through our cosmic neighborhood. Future observers who encounter these wanderers millions of years hence will find within them traces of our sun, our planets, and perhaps even molecular signatures of the biological processes that have shaped Earth's atmosphere during this brief moment when human civilization flourished. The mathematical precision underlying their orbital mechanics reveals a universe that operates according to comprehensible physical laws. Despite the vast scales involved, while the chemical complexity preserved within their structures speaks to processes of organization and evolution that operate throughout cosmic history. We live in a universe that is simultaneously more orderly and more creative than our ancestors imagined. The silence that now settles over our exploration carries with it the profound peace that comes from touching something vast and ancient and beautiful. These cosmic visitors have reminded us that we participate in a story much larger than ourselves, yet our unique perspective as conscious beings capable of wonder and understanding gives us a special role in the universe's ongoing journey of self-discovery. As you drift toward rest, carry with you the gentle knowledge that the same physical processes that shaped these ancient travelers continue operating within your own body, that the elements composing your being were forged in stellar cores and distributed through space by mechanisms that connect you directly to the deepest history of the cosmos. You are not separate from the universe. You are the universe becoming aware of itself through the remarkable emergence of human consciousness. The eternal dance continues with new movements, new rhythms, and new opportunities for wonder awaiting discovery by future generations who will look up at the night sky with the same sense of awe and curiosity that has driven every advance in human understanding. In studying the cosmos, we study ourselves, and in understanding our place within the vast web of cosmic evolution, we find both humility and inspiration for the journey ahead. Sleep well, knowing that you are part of something magnificent.